In the prior lesson, we determined how we could find the trigonometric function values of any angle between 0 and 360 degrees. In fact, we could even find the function values of any angle for that matter if we convert it to its coterminal angle that does lie between 0 and 360, which is the first rotation. But in a lot of application problems, we don't really care about where the triangle lands within the coordinate plane. All we really care about is the fact that it's a right triangle. So all of the angles, other than the right angle, will be acute angles, anywhere between 0 and 90 degrees. So let's take a look at how we can restructure or rethink the trigonometric function values. Instead of just memorizing x's, y's, and r's, perhaps it's easier for us to think about what the trigonometric function values mean in the context of the sides of the triangle. If we look to the same diagram that we used in the prior lesson, we'd recognize that we still have our side lengths of x, y, and r with the same definitions of our 6 trigonometric function values, okay? But now we're going to be looking at this from the perspective of theta. Picture yourself standing at theta and looking at the individual sides. If we do so, we could actually rename these sides based on words, names. For instance, in this one right here, we see that this is the hypotenuse. The hypotenuse is always the side opposite the right angle. Now, if we look at the side right here, I'd like you to recognize that this side is touching theta. So is the hypotenuse, but the hypotenuse already has a name. So the fact that this is right next to theta means that this is the side adjacent to theta. We're going to call that the adjacent side, or the side adjacent to theta. And notice that the side on the opposite side of where theta is obviously going to be referred to as the opposite side, or the opposite of theta. So if we got rid of the coordinate plane and all we were looking at was a triangle that perhaps was representing the height of a flagpole and its shadow, then we'd be able to actually do the trigonometric function values, not thinking in terms of y, x, and r, but instead opposite, adjacent, and hypotenuse. So now each place that we see x, we're going to replace that with the adjacent side. And anytime that we see y, we'll replace that with the opposite side. And finally, anytime that we see r will always be the hypotenuse. And this is now how a lot of students will memorize the trigonometric function values as well. Okay, so for sine of theta will be the opposite side over the hypotenuse, while cosine of theta will be the adjacent side over the hypotenuse. And finally, if you look at tangent of theta will be the opposite side over the adjacent. So the nice part about this is you really only have to memorize sine, cosine, and tangent, because as long as you remember which trig function goes with the reciprocal here, these are just the reciprocal of their corresponding values. So hypotenuse over adjacent, that's hypotenuse over opposite, hypotenuse over adjacent, and finally the adjacent over the opposite. So in order to remember which are the reciprocal functions, tangent and cotangent I think are relatively easy to remember. I'll tell you what I remember in terms of the reciprocals of sine and cosine. Each pair should have a co. So you could see that sine has a reciprocal function of cosecant, while cosine has a reciprocal function of secant. So each pair has an S and a C as their starting letter. Perhaps that would help you to recognize which one is which, okay? So with that said, let's take a look at an example of just some random right triangle and find the sine and cosine values of those. So in this given triangle, which is another special triangle where the sides are 7, 24, and 25, I'd like to mention that most triangles don't work out really nicely to be all integer values. We saw a 3, 4, 5 triangle. There's also a 5, 12, 13. There's a 7, 24, 25. These are what we refer to as Pythagorean triples because they work out to be nice integer values. Most of the time, some of the sides will involve radicals, square roots, because of the Pythagorean theorem. But we'd like to go ahead and take a look at this and recognize that even if we don't know what the angles of A and B are, we're still going to be able to find what the trigonometric function values are, or the ratios of the sides, by being given the side lengths themselves. So let's take a look first at angle A. So by looking at angle A, sine of A is the opposite side over the hypotenuse. So when you take a look at that ratio, it's simply 7 over 25. So notice that 7 over here was the opposite of A. It was the opposite side of A. All right, well, when we take a look at cosine of A, notice that cosine of A is the adjacent side over the hypotenuse. So that's simply going to be 24 over 25. So 25 is obviously the hypotenuse, but we'd like to recognize that 24 is representing the adjacent side to A. So this 24 is adjacent or next to A, while the 7 is opposite of A. And finally, the tangent is the opposite over adjacent, which is giving me 7 over 24. So we leave it as is. We don't have to write any, we don't have to find the decimal values, we just leave them as fraction values. Okay, those are the ratios of how big one side is compared to another. So let's take a look at now sine of B. So now we're looking up to B. And if we're looking at B here, sine of B is the opposite over the hypotenuse. Notice by looking at the other angle in the triangle, the right triangle, it turns out that 24 is actually the opposite of B. So sometimes that base could be the opposite side, sometimes it would be the adjacent side, depending on what angle you're looking at. So sine of B is 24 over 25, which interestingly is the exact same thing as cosine of A. So these two values are actually exactly the same. And we'll discuss the property related to this shortly. All right, well now if you take a look at the cosine of B is the adjacent over the hypotenuse. The adjacent side is 7, and the hypotenuse is still 25. But wait, the adjacent side is 7 now, when it used to be the opposite side before. And it's because it all depends on what angle you're referring to look at. So the adjacent over the hypotenuse gives me 7 over 25. Okay, so that must mean that sine of angle A in a triangle will always be equal to cosine of B in a triangle. So these are complementary angles. Notice that if this angle down here is a 90-degree angle, then A and B are always complementary angles. So that must mean that their trigonometric values for sine and cosine are going to be equal for complementary values, and that's a rule we're going to see shortly. And finally, tangent of B is opposite over adjacent, where the opposite side is 24 now and the adjacent side is 7. Okay? And so what we've recognized here that's a really important idea are what we refer to as some identities. Identities are rules that are always true. And we're going to be talking in great detail in future lessons about other identities. But we're going to start off with a couple of cofunction identities that we just learned here. It turns out that if I were to take sine of some angle, that would always be equal to cosine of the complementary angle. So it'll always be equal to cosine of 90 degrees minus that angle. Which implies that if you're talking about an angle of 30 degrees, then sine of 30 would be the same as cosine of 60. Sine of 10 would be equal to cosine of 80. And it'll always be true, based on what we just noticed here, that sometimes these sides are adjacent, while other times they're opposites, depending on what angle you're looking at. Okay? Which also implies that if you were to look at it in terms of cosine of theta will be equal to sine of the complementary angle, namely 90 minus theta. So look at the names of these, sine and cosine. Those are considered cofunctions because really you just throw a co out in front of one of them. So it turns out that there are other cofunction identities as well. Turns out that if you look at cosecant of theta, that will be the same thing as secant of 90 minus theta. So secant and cosecant are also cofunctions. And so if you were to look at that in terms of secant, that's equal to cosecant of 90 minus theta as well. So cofunctions are pretty simple to recognize because you just say the word and then throw a co out in front of it. So sine, cosine, secant, cosecant, tangent, and obviously cotangent. So tangent of theta should be equal to cotangent of 90 minus theta because they are complementary angles. And finally, cotangent of theta will also be equal to tangent of 90 minus theta. So this first example was just a demonstration of how some of these ratios repeat themselves depending on what angle you're looking at. So I'd like to look at a more general representation of this in terms of how we typically label our triangles. I believe I mentioned this at a prior lesson as well, but I do want to mention that anytime you have an angle, let's say angle A, the opposite side is always the lowercase of that counterpart. So that would mean that this would be lowercase a, while 24 would be lowercase b, while 25, or the hypotenuse, is always lowercase c. So whenever you're actually looking at this, you could also just kind of label your diagrams so that you could actually use the variables when you're computing those values. So using this identity, we should be able to create an equation or create a way to find a value of theta that would make this statement true. Now, supposedly there is some theta value to where this value is equal to cosecant of this value. Now, if you look back to our identities, there's a slight issue here. Not an issue, just something to notice, is that there is an identity here that shows that secant of something is equal to cosecant of something else, okay? All right, so that must mean a couple of things. That must mean that if I call this value A, that the only way that secant of an angle could be equal to cosecant of something is if that value is 90 degrees minus A. So there's two ways to think about this, okay? one way to recognize this is that if I were to take 90 degrees minus this quantity, that it should equal this quantity of theta plus 4 degrees. Or in other words, adding these two values together, these two angles, should give me 90 degrees because they should be complementary angles in our triangle. So if this is A, then 90 minus A would also be referred to as what we meant by B in our upper triangle. So what we could do here is we could just say, well, that must mean that theta plus 4 degrees plus 3 theta plus 2 degrees should equal 90 degrees. And so now it's just a matter of solving this algebraic equation for theta to where these complementary angles add up to give me an answer of 90 degrees. All right, well, that gives me 4 theta plus 6 degrees equals 90 degrees. And notice that every time I'm writing these numbers, I'm putting the degree symbol on there because these are angles. And so anytime I'm dealing with angles, I need to make sure that I'm putting that symbol to indicate that. So that means that 4 theta is equal to 84 degrees, which means that the angle that will make this statement true is going to be theta equals 21 degrees. So let's just check this real quick and see what that implies. What that implies is that if we write secant of 21 degrees plus 4 degrees, that should be equal to cosecant of 3 times 21 degrees plus 2 degrees. That would imply that secant of 25 degrees is equal to cosecant, and if I were to work that out, that becomes 65 degrees. And sure enough, that should be true. Because these are cofunctions of each other, secant of one angle should be equal to cosecant of the complementary angle. Now there are a few special angles, namely 30 degrees, 45 degrees, and 60 degrees, that occurs so often in trigonometry and so often in calculus and other advanced mathematics that we treat them differently, and we treat them very special in this class in trigonometry. And because their trigonometric ratios come up so often, we often want to memorize them, but we also want to be able to derive and understand where these ratios came from. So the first thing we're going to do is we're going to look at a equilateral triangle. Now the first thing to remember is that all triangles have a sum of 180 degrees. Since this is equilateral, then all 3 of these angles are equal to each other. And so 180 degrees divided by 3 means that each one of these angles is 60 degrees. Okay, so we could already see that based on an equilateral triangle, we're going to see something interesting about 60-degree angles. Okay, now just for simplicity, we could virtually make these however big or small we want to, the size of the triangle. But we're going to make the size of the triangle 2 units on every side. Okay. All right, now what we're going to do at this point is we're going to draw a line, an altitude from the top, okay, from the top here, there's a vertex, all the way down to the bottom. In doing so, we've now broken up this triangle into a right triangle. So we can now see that this is a right triangle on the left and a right triangle on the right. We can also see that by breaking that triangle up, we've now made this a 30-degree angle. And we've now made this one over here a 30-degree angle. So now, instead of calling that base 2, we could realize that this length is actually 1, and this length here is 1 as well. And so now all that's left is to find what this height is going to be. Let's just call that x. And so now by the Pythagorean theorem, we could see that x squared plus 1 squared is equal to 2 squared. By subtracting, that implies that x squared is equal to 3. And therefore, by taking the square root, we find that x is equal to the square root of 3. So notice that now that x value, that height, is actually the square root of 3. Which now means if we look at this triangle right here, this 30, 60, 90 triangle we call it, this one right here, then notice we've got a triangle with all 3 sides and with all 3 angles. Which means that we're going to be able to find the trigonometric function values of 30 degrees and 60 degrees. So let's go ahead and find that. Let's start with sine. And why don't we just find sine, cosine, and tangent? Because once we find sine, cosine, and tangent, we can also find our reciprocal identity or our reciprocal functions just by taking the reciprocal. Okay, oh, don't want to call them theta because now we're looking at 30 degrees and 60 degrees. So sine of 30 degrees, cosine of 30 degrees, and tangent of 30 degrees. And likewise, if we have sine of 60 degrees, cosine of 60 degrees, and tangent of 60 degrees, we should also recognize, because 30 and 60 are cofunctions, or rather complementary, we know that sine of 30 will equal cosine of 60. And cosine of 30 will equal sine of 60. And so at this point, we're ready to just find out what these values are. So let's start with our 30-degree angle up here. Keep in mind that in this case, the opposite side is 1, the adjacent side is √3, the hypotenuse is 2. So based on this picture, based on this diagram, and if you ever forget these values, then you could always redraw the diagram and go from scratch. But notice sine of 30 is the opposite side over the hypotenuse. But keep in mind, by the cofunction identities, that should be the same thing as cosine of 60 degrees. And we can verify that that's true. Look at 60. Cosine is the adjacent over hypotenuse. So sure enough, it's the same exact value. So now for cosine of 30. Cosine of 30 is the adjacent over the hypotenuse, or in other words, the square root of 3 over 2. And therefore, sine of 60 is also the square root of 3 over 2. So it's important to realize now that these two ratios, 1/2 and the square root of 3 over 2, are extremely important in the whole scheme of trigonometry. And now finally for tangent of 30 and tangent of 60. So tangent of 30 is the opposite over the adjacent. So in other words, it's 1 over √3. Which is technically the answer, but what we often do is rationalize the denominator. So we would multiply numerator and denominator by √3, which now means that there's a different form. Tangent of 30 degrees is actually square root of 3 over 3. How about tangent of 60? Well, tangent of 60 is opposite over adjacent, which is √3 over 1. So √3 over 1 is simply √3. So we now have the trigonometric function values of 30 degrees and 60 degrees, all based on this one equilateral triangle, okay? Now we could continue as well, as I mentioned, to find what cosecant, secant, and tangent or cotangent are, which we may as well do because they're going to be important to recognize as well. Okay, but at this point, we just simply have to take the reciprocals of each of these. Okay, so if I take cosecant of 30 and so on, we're going to be able to find each of our next values. So notice that cosecant is the reciprocal of sine, and so the reciprocal of 1/2 is 2. Secant of 30 is the reciprocal of cosine, so that's going to be 2 over root 3. But remember that we take we rationalize the denominator, which gives me 2 root 3 over 3. And finally, cotangent of 30 is the reciprocal of tangent, which really we could use either form, but it's easier to take the reciprocal of 1 over root 3, which means that cotangent of 30 is root 3. And now for cosecant, we realize that secant and cosecant are going to be cofunctions. So we know that secant of 30 should be the same thing as cosecant of 60. So that must mean that we have a value of 2 root 3 over 3. And of course, cosecant of 30 should be the same as secant of 60. And so those values are the same as well. And finally, cotangent of 60 is going to be the cofunction of tangent of 30, or the reciprocal of tangent, which means the cotangent of 60 is root 3 over 3. So we have all of these values for our 30 and 60 degree angles. Although it seems like a lot to memorize and a lot to know, we are going to be able to soon see easier ways to remember these. But I will say that the most important thing to recognize is just this real quick triangle. When you come up with your triangle, just draw a quick little right triangle, make a 60 degree angle, make a 30 degree angle. Recognize that the hypotenuse is 2, the shortest side is 1, and the tall side is root 3. And from there, you could be able to come up with what your trigonometric function values are. So why don't we take a look at the second triangle, which is a 45, 45, 90. Now, if we think about a 45, 45, 90 triangle, again, for a right triangle, 45 degrees is half of 90 degrees. So that must mean that if these are both 45 degrees, that both of these opposite sides are exactly the same. So we must have an isosceles triangle. So for the same reason we did before, it can be helpful to either, we could call these 2 as well. It doesn't really matter. I mean, if we just keep these the same as we did in the last one, we keep these 2 and 2. But it's often helpful to just keep them as 1 and 1, and then it makes it a little easier to actually calculate what the hypotenuse is. So in a very similar way to what we did in the last one, we're going to say 1 squared plus 1 squared is equal to, well, we'll call it x for now, is equal to x squared, which means that 2 is equal to x squared, which means now x is the square root of 2. So if x is equal to the square root of 2, we're now able to use those 3 sides to find out what all of the trigonometric function values are for 45 degrees. So when I look at sine of 45 degrees, it doesn't really matter which angle we look at, because sine is going to be the same thing regardless of which angle you look at. And so sine of 45 degrees is going to be opposite over hypotenuse. But since we rationalize the denominator, the more common value is root 2 over 2. So this is, again, the ratio of the y value compared to the hypotenuse. As for cosine of 45, notice that it's the adjacent over the hypotenuse. But notice that 1 is the opposite side, but 1 is also the adjacent side. So this is a special triangle because notice the 2 legs are equal. So sine and cosine are going to actually give you the same exact values. This is the only angle where this will happen, where sine and cosine are exactly the same. The only acute angle. There is another angle in another quadrant that will be very similar. And finally, tangent to 45 will be opposite over adjacent, which is just simply 1. Well, once we have these three, we could find the other three pretty easily. The reciprocal of 1 over root 2 is root 2 over 1, or just root 2. And obviously, secant of 45 is going to be the exact same value as cosecant. And finally, cotangent of 45 is obviously the reciprocal of 1, which is also 1. So again, even though there's a lot of ratios to try to remember for these special triangle or special angles, when it comes down to it, you just have to remember how to construct the special right triangles that are going to help you to find what these ratios are. Now I've determined a way to create a helpful table to help you remember each of these values. So, so the way that we're going to do this is we're going to, first of all, write up our special angles right up here, 30 degrees, 45 degrees, and 60 degrees. Okay. And I'm going to start just with sine of theta. So when I take sine of theta and I look up around this way and I kind of cross-reference the angle with the trigonometric function value, okay, then the sine of theta is going to be 1/2. And if I know that sine of 30 degrees is 1/2, then sine of 60 degrees is the other special ratio of root 3 over 2. And like we just saw in the last triangle, sine of 45 degrees is root 2 over 2. But keep in mind that the ratios for the cofunctions are going to be similar. So I can realize that this one over here, cosine of theta, can actually work around this way. And now I should recognize that if sine of 30 degrees is 1/2, then cosine of 60 degrees is 1/2. If sine of root 3 over, if sine of 60 degrees is root 3 over 2, then cosine of 30 degrees is root 2 over 2, or is root 3 over 2. And lastly, the 45 degrees is right in the middle because both angles are the same. And so now we can go on to our tangent row, to where this is tangent theta. Okay. And now if I take tangent, okay, tangent of 30 degrees, if we refer back to our original triangle, remember that tangent of 30 degrees was root 3 over 3, while tangent of 60 degrees was root 3. So we can now fill those in and recognize that tangent of 30 degrees is root 3 over 3, while tangent of 60 degrees is root 3. And we just recognize that tangent of 45 degrees is 1. But notice that those are going to be the same values as cotangent of theta, except for our opposite or our complementary angles. And so our cofunctions are going to be listed on the right, while our non-cofunctions are listed on the left. Okay, and so we've got cosecant of theta over here as well. And so if I take a look at secant of 30, remember that that was just going to be the reciprocal of cosine of 30. Right? So notice that this is going to be 2 root 3 over 3. While secant of 60 is the reciprocal of cosine of 60. Okay, cosine of 60 is 1/2, so this is going to be 2. And finally, when we look at secant of 45, that's simply going to be root 2. So there's really only 9 values that you have to remember, but technically, it turns out that the only ones that are really going to be most important moving forward, because once we know these, we can find the rest, are sine and cosine. As long as we know these 3 ratios by heart, we're going to be able to find all the rest of them coming up here shortly. Now, before finishing up, one thing I would like to do is to make sure that we recognize that even though we could do this on a calculator, sometimes we need to, but because we don't know what the trigonometric function values are for certain angles. But anytime we're dealing with these three special angles, we always want to make sure that we're giving exact values. And if we're given information about the sides of a triangle, we also want to give exact values. Well, let's just take a look, for instance, tangent of 30 degrees. Okay, so the way that we're going to do that is we've got to type in tangent of 30 degrees. Now, the first thing to recognize on whatever calculator you have is that you are in degree mode. It'll say DEG typically, or D. Another mode would be radians. And oftentimes, whenever we're dealing with this, we are going to be learning about radians at a later time. And it'll be more important to make sure that your calculator is normally in radians. But you've also got to make sure that you are paying attention to what the units of measure are. So now we're going to punch in tangent of 30 degrees. So some of you have to type in 30 and then hit the tangent button. Some have to hit tangent of 30 degrees. So let's just take a look at that for a second and recognize that tangent of 30 degrees gave us an approximation on our calculator of 0.57735. 0.57735, and so on. Okay? But notice that we already calculated from our exact value that that decimal is actually the square root of 3 over 3. And if we were to take the square root of 3 over 3, the square root of 3 divided by 3, we still get something close. But I'm going to take a look at the very end over here and realize 196. If I were to just type in 30 over here, you would still get 196. So it looks like it's the same value. The problem is, by putting 0.57735 and stopping there, you're not giving the exact value, which is this infinite irrational number. And so when you have a choice in trigonometry, always give the exact value as a ratio.